So in the last video, we saw Bayesian games for the first time, and I told you that the idea behind Bayesian games is that we're going to model incomplete information about payoffs, let's say uncertainty about payoffs, but I didn't give you any actual details of how to do that. So let's see how this works. So here's a kind of baby example. Suppose we want to model a variant of the prisoner's dilemma where player 2 believes that there's a chance that player 1 might hate defecting with some probability. So we kind of have two worlds. We have one which is an ordinary prisoner's dilemma where both players have the payoffs as in the ordinary prisoner's dilemma. And then we have another world where player 1's payoffs are modified so that they get a penalty whenever they defect, and this kind of models their preference to not defect. So we're going to give player 1 two types, which are called type 1 and type 2. And then, so player 2 is only going to have one type. They're going to be the ordinary prisoner's dilemma player no matter what. If you remember that payoffs depend on the moves of all players and the types of all players, so that means that to completely specify the payoffs in this game, we have to give essentially two copies of the payoff matrix of prisoner's dilemma, one for where player 1 has type 1, and that's the ordinary prisoner's dilemma, and then one where player 1 has type 2, and that's one where whenever player 1 defects, I've subtracted 2 from player 1's payoffs, and this models that they hate defecting. Okay. So to fit this into the definition, we still have the moves for both players are cooperate and defect. Player 1 is going to have two types, 1 and 2, where 1 is normal and 2 is hate defecting. Player 2 is going to have only one type, which is normal. And now we're going to have a common knowledge prior. So that is to say, we could have the combination of types 1, 1 with probability, some probability mu, and combination of types 2, 1 with probability 1 minus mu. So these two are all of the combinations of types that could happen because player 2 only has one type. So when I say common knowledge, what I really mean is that this is going to be player 2's belief about player 1's type in practice, but also that player 1 knows it. Player 1 knows that it's player 2's belief, and player 2 knows that player 1 knows that it's player 2's belief, and so on. And so we're going to get a payoff function with this type, which is just given by the matrices that I wrote here. So we can slightly more usefully draw this as an extensive form game. So here we have the combination of types 1, 1 with probability mu, and the combination of types 2, 1 with probability 1 minus mu. And then we have two bimatrix games here. And I've set up the information sets here so that player 1 knows their own type, but player 2, so all of these 4 nodes are all in one information set. So player 2 knows nothing. They don't know player 1's move. They also don't know the type. Of course, they know their own type, but there is only one. And then the payoffs are given down here. Okay, so in the next video, I'm going to show you an appropriate solution concept that's specialized to Bayesian games called Bayesian Nash equilibrium. But for now, we can solve this informally with kind of common sense. So when we imagine that player 1 is type 1, we know that defecting is a dominant strategy for them. So we know that. So remember that as pure strategy for player 1 is going to be a mapping from their type to their move. So because defecting is a dominant strategy for type 1, it's reasonable to think that their strategy is going to, in type 1, it's going to play D. Now, also, if we look at the payoff matrix for type 2, I've set it up so that C cooperates as a dominant strategy for player 1. So we'll see that in both cases, no matter what player 2 does, if player 2 cooperates, then player 1 prefers cooperating because 2 is greater than 1. And if player 2 defects, player one prefers to cooperate because 0 is greater than -1. So that means that it's reasonable to say that the function that in type 1 plays D and in type 2 plays C is a dominant strategy for player one. What that means is that we can kind of eliminate the three strictly dominated strategies for player one, and so we can reduce this game to this thing. So all I've done here is I've removed all of the this subtree and this subtree. So we get back this thing. So let's just say player two. So player two doesn't know the type, but they know that if the type is 1, then player 1 will definitely defect, and if the type is 2, then player 1 will definitely cooperate. And player 2 doesn't know, but they know the prior, which is that they are here with probability mu and here with probability 1 minus mu. So at this point, what we can do is we can calculate player 2's expected payoff for each move. So we find that if they cooperate, then they get this payoff 2 minus 2 mu, and if they defect, they get 3 minus 2 mu. So it turns out that that this one defecting is always higher. So in fact, defecting is actually going to be a dominant strategy for player 2 in this situation. So we can solve this game by form of iterated deletion of dominated strategies.